This is basically going to be a tour through all the steps on building and productionizing retrieval-augmented generation systems, right? And so this is using large language models to basically build both basic to advanced applications over your data. So by way of introduction, I'm Jerry. I'm co-founder CEO of Llama Index. Llama Index is a framework. At a very basic level, it's a Python library, right? To basically help you connect your large language models with your own sources of data to build various types of applications. So let's get started. I think these days, in the world of generative AI, obviously it's exploded in popularity around this time last year, actually. And within the past year, there's been a lot of interest, especially among enterprises, in building different types of use cases on top of large language models. Some of the most popular ones we're seeing include document processing and extraction, so being able to extract structured outputs from unstructured documents, knowledge search and question answering. So that part is pretty core to this idea of RAG, or Retrieval-Augmented Generation. Conversational agents, or chatbots, basically a ChatGPT-like experience, but over maybe a data source, as well as workflow automation. So, given some sort of flow, like, can you actually get a large language model to just execute it instead of you having the human in the loop? So the overall context, maybe just taking a step back, is that large language models are a phenomenal piece of technology for knowledge generation and reasoning. You open up ChatGPT in a browser, you can ask it basically a lot of different things, and it'll give you back an answer, right? You can ask it to debug like Python code. You can ask it articles about, or basically anything on Wikipedia. You can ask it to generate like a poem for you in the style of a famous poet. But it's pre-trained on large amounts of publicly available data. But as people are using ChatGPT or similar experiences, you're finding that there's a few different use cases that are emerging, like question answering, text generation, summarization, and planning. And pretty much ever since the start of last year, people started asking themselves the question, how do you actually augment language models with our own private sources of data? This includes anything from raw files, like PDFs on your hard drive, to like common services that you use, like Notion, Slack, to databases, including both SQL databases, like traditional data stores, as well as kind of like the newer age of vector databases as well. And so given all this data, right, whether I'm a developer or an organization, how do we best augment language models with it? A few paradigms for inserting knowledge have emerged. One idea is retrieval augmentation, where you actually fix the model and then you put the context into the prompt. So in this setting, basically, and this is a setting we'll probably focus on, you have the language model, OpenAI GPT-4 Turbo, and we don't actually train it anymore. We have our own sources of knowledge, let's say a bunch of Notion essays, and we figure out how to actually take all this context from your Notion essays and put it into the input prompt, right? And maybe you have like gigabytes of data or just a lot of text data within your text corpus, but you need to figure out how do you actually figure out how to retrieve the most relevant pieces of text to put it into the input prompt. And we'll go over this in just a bit. The other paradigm, of course, is fine tuning. We'll touch on it briefly within this slide as well, or within this talk, but it's basically, you want to actually train the model itself, update some portion of the model weights to try to incorporate new knowledge. The way I think about Llama Index is it's a data framework for LLM applications. It basically helps you, it gives you the tools across the lifecycle of actually connecting your data with LLMs. This includes three main components. Starting from your data sources, we first want to ingest the data. We mostly do this through our community-driven site called Llama Hub, which has over 150 plus data loaders. We have a variety of different other integrations on there too, but basically this is a starting point to allow you to load in different data sources. The second piece is processing them into a storage system. So how do you store and index your data for different types of use cases? And these indices, this data storage, this is where Llama Index got the name from, is specifically designed to actually feed it into the language model. And of course, number three is then how do you actually retrieve and query over this data and use it in conjunction with your language model of choice. And this includes the variety of use cases I talked about, like question answering, summarization, agents, and more. We'll actually go through this in just a bit, but basically to set up some sort of question answering, it's very simple. You load in some data. Second step is you index stuff, right? Like you index a set of documents. Third is you can start asking questions over it. So in around 5 lines of code, without really needing to know what's going on under the hood, you can basically get some sort of question answering like system over your data. First, let's talk about kind of this idea of retrieval-augmented generation and how it works. So we'll go over the RAG stack. The current RAG stack for building a question answering system mainly consists of 2 main components. One is data ingestion and parsing, and the second step is data query. So in data ingestion and parsing, you start off with some source documents. And then what you want to do is you want to chunk up these documents into a bunch of slices. And then you embed each slice and put them into, for instance, a vector database. And then once the data is in a vector database and embedded, then you do retrieval and synthesis, right? So to go over this in more detail, in the data ingestion and parsing stage, we want to take in some documents and split up the documents into roughly even chunks. And there's different types of parsing strategies for this. Each chunk is just like a slice of raw text from the original document. You generate an embedding for each chunk, like OpenAI embeddings, sentence transformers, and then you put each chunk into a vector database. In the second part, once the data is actually in the vector database, then you want to do retrieval and synthesis. You first want to find the top k most similar chunks from the vector database collection, and then you plug these chunks into the LLM response synthesis module. Now let's talk a little bit about how this response synthesis module works, right? Because in this stage right here, you're feeding in all these text chunks into the context window of the LLM. And then some natural questions arise like, okay, but what if the context window actually overflows? What if I actually have 5,000 tokens of retrieved context, but the context window itself actually only handles 4,000 at most. So because without that, otherwise you would just stuff this into the prompt, right? You just literally put it into a giant text string and then call the LLM, and that's pretty trivial to do. So there's kind of 2 strategies that have emerged, and there's more too, but there's different types of response synthesis strategies to basically summarize or over larger amounts of context that overflow the context window. One basic strategy is this idea of create and refine, where you take each chunk, pack as much as you can into each context window, and then consider them as nodes. So for node 1, you first synthesize an answer over node 1, right? This is the initial chunk of text that can actually fit in the context window. Given the query, you get back an initial response, and then you feed this response along with node 2 and every subsequent node and the query back into the LLM, right, to continue generating a response. So it's you first generate a response from node 1, and then you continue refining it as you go on through the subsequent nodes until you get back a final response. Another idea is this idea of hierarchical summarization. We call it tree summarization and llama index, but basically, assuming you have a bunch of nodes, which both all fit into the context window, you could hierarchically generate answers until you get back a final answer at the end. This strategy tends to lead to slightly more coarse-grained text generations, just because you're kind of continuously re-summarizing things. But at the same time, this can also be pretty parallelizable because you can run all these in parallel LLM calls. So with that said, this is what the basic RAG stack looks like. And we'll go over this in, this is basically the quick start tutorial of Llama Index, but we'll kind of just viscerally show you how this works. First we want to pip install Llama Index. So this is a Python package. It's available on PyPy. And so definitely encourage all of you to check it out. For the purposes of this notebook, I probably just won't be running the cells itself, but I'll just walk through the steps and show you how it works. So one of the first things you do is, from LLM-Index, import all the necessary components. I'll go over this and what they mean in just a bit. But we'll load our data source. That's step one. And in this case, we're going to download Paul Graham's essay, right? This is one of his popular essays. The title is What I Worked On. It was released in February 2021. And we load it in through one of our simple utility functions, like the simple directory reader, which will load in a text file. Here we just have the file sitting in our Dropbox in plain text. But this is the full essay, right? It's just a big text file. It's not the biggest, actually. It's like 10,000 something tokens. And there's definitely bigger data sources, but at the same time, you can kind of get a sense of how this works. And so assuming a 4,000 token window limit, this would definitely not fit. Nowadays, given the token windows have increased to 100K, we kind of need a bigger example. But for the purpose of the demonstration, this is how it works. The second step here is we're going to call index equals vector store index from documents. This is essentially the ingestion and indexing piece of that RAG stack that I mentioned. So, and here we hide a lot of it under the hood, but within LLM-Index, we have the abstractions to basically allow you to compose your own ingestion pipeline if needed, right? This is just like the black box method if you don't want to actually do that under the hood. And so by doing this, what you'll do is chunking and embedding and indexing. You'll take in these documents or this one document, split it up, embed each chunk, and actually put it into the storage system. The next step is now you want to get back a query engine, right, over this index. Now that data is indexed, you can now run some sort of query over that index. And here you see the response, query engine.query, what did the author do growing up? You get back some response. And this is the generated response. And this follows that second step of or the query part of that RAG stack, right? Where you do retrieval with a top K equals 2, and then put it into the context window of the LLM, and you get back this answer. The author mentioned that before college, they wrote short stories, wrote programs on the IBM 1401. And so not only can you get back the response, you can also print the source nodes. And one of the main requirements for basically building Gen AI applications is that you have proper accountability and transparency in sourcing, right? So that you actually kind of understand what's going on. In this step, we show that this is the specific chunk that's actually been retrieved to help you answer the question. Okay. Now, jumping back, that was a quick overview of how the basic RAG stack worked. And so now let's talk about some challenges with it, right? So in what cases does this actually fail? And if you've set this up yourself over the past year, using a framework plus an LLM plus a vector store, chances are you might have identified failure cases yourself as well. The way I think about challenges with naive RAG is there's different types of failure modes. There's stuff that is quality related, like you're actually just not getting back the right responses given the questions that you're asking. And there's also non-quality related stuff too, like latency, cost, and syncing. So in terms of response quality, there's a few different properties of bad responses. The first is bad retrieval. And there's a few aspects of bad retrieval. This means that given a question, you're not actually returning the relevant chunks. And of course, if you're not returning the relevant chunks, you're not going to get back a good generated response, right? And a lot of times this retrieval process is completely independent of the capability of the LLM itself. The LLM can be very, very good, but if you don't get back the right answer, you're not going to synthesize the right response. So a few different properties here. One is low precision. Not all the chunks in the retrieve set are relevant. And so this means that you might have a lot of noise in the retrieve context. You might just get back a lot of fluff. And the issue is that if you get back a lot of fluff, depending on the LLM you're using, some LLMs are better than others at identifying the relevant information within a mess of text, and some are pretty bad at it. And so what this can run into is the LLM can end up hallucinating, right? Give you some answer that's unrelated to your question, because of all the noisy context. There's also lost in the middle problems, which are a common problem at this point, identified with a variety of different LLMs, where if the relevant context is somewhere in the middle of a context, the LLM tends to have trouble finding it, right? And you can look at analysis. This applies to LLMs with large context windows too, like OpenAI, Anthropic, all these, like the 128K, 200K context windows. If you actually stretch it to that amount, you'll find that a lot of information starts getting lost in the middle, right? So this is the issue of returning too much context when you actually try to set up these systems. So more context is not always better. The other aspect is low recall. Not all the relevant chunks are actually retrieved. And here is where, given your retrieval algorithm, maybe it's top K embedding lookup, you're not actually getting enough context for the LLM to synthesize an answer. The next aspect here is bad response generation. And so even if you get back, for instance, the relevant results, and of course, like some of this is a function of low precision, low recall, you might actually end up with some LLM failures. And a lot of this is due to the model itself. You might get hallucination issues. The model might make up an answer that's not actually in the context. You might get irrelevance. The model sometimes comes up with an answer that doesn't actually answer your question. And of course, depending on some cases, the model might make up an answer that doesn't actually, it could be harmful, offensive, or it just generally doesn't actually adhere to guidelines that you set, right? And that's probably the more general problem. You prompted it to output things in a certain style, or even have like structured outputs, and it just didn't listen. So given these failures, we have to think about the type of software system that we're building, as well as like levers and knobs that we can tune to try to actually improve these systems. What's very interesting here is that if you've ever done machine learning before, this part is pretty similar to machine learning, right? Just the hyperparameters of a machine learning model. When you build an LLM software system, you have the LLM right here, and you're basically wrapping it with a bunch of different chunks, different pieces, different modules that combined kind of create this higher level black box system. You have your documents, your chunking retrieval strategy, your embedding model, and of course the LLM, and like stuff like the prompt template as well. All these are parameters that affect the performance of your final result, given any sort of input question. And so unlike traditional software systems, you can't really reason about stuff in isolation because all these are parameters that affect the final end performance, and they're kind of stochastic black boxes. And so to categorize like the set of parameters that you can actually tune, there's data, like can we store additional information beyond raw text chunks? There's embeddings, can we optimize our embedding representations? There is retrieval, can we do better than top K embedding lookup? And there's the synthesis piece. There's the prompts used for the LLM, as well as like, can you actually use the LLM kind of more along the retrieval piece or even have more agentic strategies? Of course, before you try out any of these things, and very similar to traditional machine learning, is the fact that you need some sort of evaluation data set. The main difference with traditional machine learning is that you don't need a training data set because you're not actually training the model. And so typically when you use like, sklearn or like PyTorch or whatever, you typically set up both a training and eval set beforehand because you have a data set and you do some split and then you allocate 70% to training, 30% to evals. The main thing with LLMs is that you don't really need a training data set to get started at all, but you do need an eval data set. And so basically in like the mind space of a developer, they need to allocate some time to basically think about, I need to allocate some time to gather an evaluation data set to actually try to evaluate, measure the performance. So in terms of evaluation, let's talk about it because how do we actually evaluate a RAG system? And how to what extent is this challenging and how is it different than, for instance, evaluating a traditional ML system? So a RAG system, to simplify a little bit, has two main components. There's one, the retrieval piece, and two, the synthesis piece, right? You can have more complex systems too, but this is the thing we'll start with. You can evaluate in isolation. So you can evaluate retrieval in isolation. You can also evaluate synthesis in isolation. You can also evaluate this entire system end to end. There's an open question of whether you should start with end-to-end evaluation or evaluation in isolation. I think I've wavered back and forth on this. Right now, my current leaning is, maybe you should just evaluate end-to-end first, just to validate on some like 50 data points, 30 to 50 data points, whether or not your system is generally working, right? And then based on whether it's not working, you can go in and try to actually isolate like the source of the failure, whether it's retrieval or the prompt. But in terms of like, how do we think about retrieval evaluation, right? What is retrieval again? Given a query and given the retriever, you get back a set of retrieved IDs. Basically, this corresponds to the text chunks. And the high level goal of retrieval should be that given the query, you return the most relevant chunks. And so if you actually have ground truth of what those relevant chunks are supposed to be, you can evaluate the predicted rankings of these chunks against the actual chunks using some sort of ranking, or the ground truth chunks using some sort of ranking metrics, right? So if, for instance, these are the expected IDs, you can compare the predicted against the ground truth using, traditional ranking metrics like success rate, MRR, this should say NDCG, but a variety of these things. And this is not really anything new. This is something that's existed before. Maybe one thing to consider, though, is that ranking metrics and retrieval, like the quality of your retrieved results, don't necessarily completely correlate with generation performance. Even if things are in the correct ranked order, because of the way that LLMs actually attend to this context, where they forget things in the middle, it's not actually guaranteed that this is the best ordering to give to the LLM, if that makes sense. Sometimes, and that's something that we haven't fully explored yet, but it's just some intuition to be aware of. Evaluation end-to-end. So here is, given a user query and given the entire RAG pipeline, try to and given the generator response along with some context, try to evaluate how good the generator response is, right, according to a variety of different factors. If you have the ground truth answer, you can evaluate, for instance, correctness, whether or not how much the predicted answer matches the ground truth answer. Without the ground truth answer, you can evaluate stuff like how much the response matches the context, how much the response matches the query. All these are just pieces of text, which means that you need some way of actually measuring how good this piece of text is in comparison to another piece of text. And so you can use traditional heuristics for this, like kind of numeric metrics. I think these days there's a lot of folks that are very interested in LLM-based evals. And there's some papers where, like GPT-4 can be a relatively reliable human judge. And as these models get better, they'll probably get better at being able to judge things. And so a lot of these metrics are dependent on actually calling an LLM under the hood. A little bit more about this, like GPT-4 is a good human grader. I think this is a good article from Databricks a few months ago. But basically, like if you take a look at kind of human versus GPT grading assignments for some of these, for like scoring like how good GPT 3.5 is, there's like a decent correlation there, right? And so if we apply GPT-4, for instance, as an LLM eval grader, we can ask it to do a few different tasks. Some examples are correctness, like whether the response matches the golden answer. So you can just prompt GPT-4, given these two examples, how much one matches the other. You can prompt it for faithfulness. So whether the response actually matches the retrieved context. This will test for hallucinations mostly, right? So given some context, if it doesn't match, this means that it's roughly hallucinating. Relevancy, whether the response actually matches the question. So whether it actually gives an answer. And of course, like guidelines, whether it matches guidelines. Great. So we talked about basic RAG. We talked about how to do evaluations because that gives you the basis from which you can experiment with some more advanced techniques. And now let's talk about optimizing RAG systems, right? And so we'll go into this section, talk about some basic levers you can pull, and then we'll talk about the extensions here. Like we'll talk about general ways to kind of extend beyond this, and this includes fine-tuning and agents. There's a variety of things you can do, and these are all practices that have emerged over the past year in terms of trying to optimize your system for better performance. You have this question answering bot set up, the 5 lines of code in LLM index. Here are a lot of things that you can try. On the left side of the axis, you see things that are easier to implement, typically have lower latency and costs. And these are kind of just like table stakes things you can try. So you're not going to make like step changes in the performance or capabilities, but hopefully you can like tune some parameters and make it work better. On the right side of the axis, like this is stuff that is more expressive. Like some of these things will actually lead to big step changes in the capability of your entire pipeline and answering more advanced questions. But they typically are harder to implement. And a lot of times, especially the agentic stuff, as well as fine tuning, they incur higher latency and costs. Like fine tuning is a one-time fixed cost. Agentic stuff tends to incur high latency at query time. So let's first walk through some table stake stuff, right? In terms of things that just levers or parameters you can tune to actually improve performance. The first is chunk sizes. Tuning your chunk size can have outsized impacts on performance. And so for like, if your chunk size is too small, let's say your chunk size is like 100 tokens, which is like 80 words or so, and your top K is equal to 2, that's not a lot of context for your LLM to actually work off of. So if you do retrieval, you retrieve 160 tokens of context, and the LLM just doesn't have that much information to answer a question, it tends to not give you very good answers. On the other hand, if your chunk sizes are too big, one, it's going to cost you more money and be slower. But two is, again, going back into the loss in the middle problems, like this might actually end up confusing the LLM because the relevant context is somewhere in the mess of retrieved chunks. So it's not obvious that more retrieved tokens actually equates to higher performance, right? And so typically there's some sort of like U-shaped curve in basically error rate versus like chunk size. And the optimal chunk size is somewhere in the middle, right? There's not necessarily a good universal chunk size for everything because it really depends on your use case. I think for basic question answering tasks, our defaults are around 1,000, and that tends to work pretty well with a top K equals 2, but of course you should tune that. Another basic like table stakes thing is prompt engineering. I think we've tried pretty hard to make sure that basically all these prompts that are used within our RAG pipeline are exposed to the user. We also have integrations with observability providers, like for instance, like Arise Phoenix, Weights and Biases, OpenTelemetry. And these allow you to trace all prompts and LLM calls going in through the entire system, along with other stuff like retrieval calls as well. And so I highly encourage all of you, if you're building these pipelines, to try to use some of these tools. And a lot of these, you can integrate with LaMDAX in literally one line of code to give you more visibility into what's going on under the hood. So for instance, and we talked about response synthesis at the beginning portion of these slides, the prompt template typically looks something like this, like context information from sources listed below, you have some context. And given this information, try to answer the question. And then here's the question. There's ways you can customize this prompt template, right? You can try making it, add some special tokens that are model dependent. This prompt is typically optimized for like OpenAI, tends to work less well maybe on other models. And sometimes you have like special formats or like instruction brackets that you need to add to the prompt, right? To basically, because it's been pre-trained on that type of data. So for instance, like Llama 2, Anthropic, a lot of these require like custom brackets. Another way is you can add like few shot examples. For instance, if you're trying to get structured outputs, like if you're trying to get the model to output something in a JSON format, or you're trying to get it to output stuff in a certain style, adding both positive and negative examples to the prompt itself tends to help the model in really understanding whether or not whether or not the output format is correct. And so it helps to enforce more reliable outputs. Other ways of customization include, there's a paper that came out like a few weeks ago to like a month ago where you can try to add like emotions to the prompt. And it's a pretty funny paper because basically it turns out that if you really try to, appeal to make the LLM feel bad, basically, it tends to lead to higher performance. But you can try that out at your own risk. The model itself, the LLM, of course, is quite an important step towards being able to have a performant RAG pipeline. What we did within Llama Index is we integrate with like 20 plus LLMs, right? Like we integrate with all the open source models as well as all the paid, popular paid models. Um, and we ran some basic benchmarks to understand what their capabilities are on easy to hard tasks. So if you look at, and this might be a little small, but if you look at the columns here, for instance, here the columns are easy tasks to harder tasks like data agents. And on the rows, you see the model name. These tasks include like the basic RAG pipelines to the router query engine, to what we call like a sub-question query engine based some basic planning capabilities, to text to SQL, structured output extraction, as well as agents. And here, like check marks show whether or not this model is actually capable of doing this over a pretty simple data set. This is just like the Llama 2 paper. And red means that it doesn't actually give you the right results. And then the warning sign means it's kind of inconsistent. So the task performance on easy or hard tasks varies wildly among different LLMs. Currently, one of the best models that we've seen is Zephyr, and of course Mistral. And these on the open source side are 7 billion parameter models that actually exhibit decent properties in terms of some aspects like structured output extraction, text to SQL, as well as agentic behavior. The paid LLM APIs typically will do better in terms of performance across the board. Like GPT-4, of course, like does well in pretty much everything. GPT 3.5 tends to do okay on tasks, but is a little worse on agentic stuff. And of course, there's like the Claude models from Anthropic too. There's also, of course, being able to customize your embedding model. And we've since updated these numbers, and this is on a very toy data set, so definitely don't kind of take these numbers as is. Definitely run it over the data that you have. But the embedding model and the rewriting quality significantly affects how good your retrieval is. Right? And so different models like OpenAI Ada tends to be one of the leaders in actually giving good results. There is, of course, Gina, Voyage, Cohere v3. All these which have become competitive with or even surpassed the capabilities of the Ada model from OpenAI. And so you should definitely try out different models, see what makes sense for you in terms of cost and latency. But some of these models will do better than others in actually giving you back relevant context from your text. Another example of something that's pretty table stakes is metadata filtering, right? So metadata filtering is, or maybe to take a step back, metadata is context that you can inject into each text string. So if you imagine just a block of text, metadata could just be like a JSON dictionary that you append on top of the text. Some examples, this includes very simple types of data as well as more complex types. This includes stuff like page number, document title, a summary of adjacent chunks, questions that the trunk can answer. Some benefits of this, this can help retrieval. So if you actually inject the metadata into the text, a lot of times that actually gives you back the relevant answers or the relevant chunks. This can help augment response quality by having the metadata in the text itself. You can actually give the LLM more information from which it can do stuff like cite sources, augment the response with more context. And having this metadata also integrates with structured filter capabilities within vector databases. So one general thing to think about as metadata is most of the world runs on semi-structured data. And so even if you have a bunch of raw text chunks, chances are there's going to be structured information that you can and probably should append to your data. And you can basically, within Llama Index, have control over whether this is used during the retrieval or synthesis step or used as part of a metadata filter. An example here is, let's say you have a bunch of financial documents. They're all stored in a vector database. And then let's say you were just running like top K retrieval using raw semantic search from the vector database. You ask a question, can you tell me the risk factors in 2021? Raw semantic search is low precision, right? And so given a query string, you are going to ask this entire collection of 10K document chunks, and they're literally just raw chunks of text. And let's say you get the top 4 most relevant chunks given this question. there's just no guarantee you're actually going to get back the relevant document chunks from 2021. You might get back stuff from 2020, 2019, and what we found is typically if you just run pure raw semantic search for these types of questions, you're not really getting back a lot of relevant information, and this ends up confusing the model. An idea here is, okay, but what if, given this type of question, and the fact that these vector databases actually support metadata filtering. And by the way, what is metadata filtering? This just means that, given some sort of query to a vector database, you can also specify a set of filters. And it's basically a where clause in a SQL statement. And you'll first filter by these filters, these metadata filters, and then run semantic search given the query within the filtered data. So it really kind of makes your retrieve set more precise, because all the stuff that's outside the set is just irrelevant. So given a question like this, if you can actually infer the metadata filters, like given this question, infer that, we want to filter year equals 2021, then you can remove the irrelevant candidates in the first pass, and this will actually increase the precision of the retrieve context, right? To basically guarantee that you have the relevant results. A general concept here, and we'll kind of do 2 slides in advanced retrieval. And so this is moving a little bit beyond table stakes and a little bit more towards kind of thinking about stuff that's a little bit more involved. One of these concepts is small to big retrieval. One of the intuitions about this whole process about taking in a document and splitting it up into a bunch of chunks is that embedding stuff, like embedding just chunks themselves, feels pretty suboptimal. You have like delineated the boundaries of these chunks beforehand, right? And these chunks are are typically very arbitrary. You're splitting on sentences, you're splitting on paragraphs, and sometimes context might actually carry over between different chunks, and you're kind of cutting it straight down the middle. So a lot of times what actually helps here is what we call kind of like small to big retrieval, where you first actually embed the text at the sentence level. And then you retrieve text at the sentence level. So when you get given a question, return the most relevant sentences given your question. But before you actually feed this to the LLM, you expand that window during LLM synthesis. So you have an expanded window of text around the central piece of relevant context to actually feed to the LLM context window, right? And why is this interesting? It's decoupling basically the chunk that you have for retrieval versus the chunk that you use for synthesis. And the original assumption was that they're one and the same chunks, but here you're actually retrieving a smaller chunk and feeding a bigger chunk into the LLM synthesis piece. We found that this idea actually leads to generally better performance. Here's just a very qualitative example. And of course, you can run this on your own data set as well. We've run this across a variety of just very basic data sets and typically have found better performance by doing this. Here in this example, with sentence window retrieval of top k equals 2, you get back a proper answer. With naive retrieval, because you're just returning kind of these arbitrary text chunks, with k equals 2 and even k equals 5, you're not actually able to get back a good answer. And so this is just more of a visual diagram showcasing how this works. But if you take a look at, for instance, like this piece right here, the way it works is you can think about like a smaller chunk as a reference, like a pointer to a bigger chunk, right? So you index or retrieve the references, but then the actual thing you feed to the LLM is the thing that's like dereferenced or the bigger chunk. And here is just maybe one general comment on an example like advanced retrieval architecture that you could build, right? And this draws lessons from existing retrieval best practices, as well as kind of of course like the RAG stack itself in past year. This general idea is like the RAG fusion retriever, which combines best practices around retrieval with, of course, the LLM at the end to generate a final answer. And the interesting thing here is seeing how you take some of these like traditional retrieval practices and actually have the LLM at certain steps here to actually help augment the capabilities of the entire pipeline. If we think about generally what are good practices around retrieval, the first is given a user query, actually try to translate or rewrite that query into either subqueries, like decompose it into a bunch of subproblems, or actually, given your knowledge about the context, translate it into something that's more amenable for retrieval. Right? And so, given this question, you can actually do this query generation using an LLM to generate these subqueries. Before, you could use like traditional models, heuristics to rewrite these queries. Here, you can actually just prompt an LLM. And this is one step, and you generate a set of parallel queries. Now, for each query, one idea here is this idea of like ensemble retrieval, actually. And this is something that's kind of been around in traditional retrieval settings too. But assuming you have a bunch of different types of retrieval modes, like you might have like something that does semantic search, you might have something that does like hybrid or keyword search, you might have something with like a different top Ks or maybe even like a different neural net architecture or a different embedding model. You run this query in parallel across every retriever and get back a set of retrieve results for every node or for every retriever. Okay. So let's say the top 3 from every retriever. The third step is this idea of fusion, re-ranking. Pretty much every production grade retrieval system out there uses some form of ranking or re-ranking after the initial pass. And this is what we call fusion. And there's some different algorithms that you can use to actually try to fuse the original set of retrieved nodes into the new set. But the idea here is, you have some input set of candidate set of retrieved context. It could be very big. The top K could be very wide, like in the tens or hundreds even. And you run some sort of re-ranking algorithm on top of that to both filter down the set as well as reorder the context or the priority of each node. And finally, given the filtered re-ranked set of nodes, you actually synthesize and get back a response. This is a pretty good reference architecture around advanced retrieval. Of course, given everything that I just said, like every use case is a little bit custom. But if, for instance, you're interested in diving into just a general architecture around better retrieval, this is something I would encourage you to look at, right? These are just some best practices. You can combine it with the LLM, and this will probably give you better results than just doing the top K. And of course, this might actually be a little slower though, because you're involving more steps in this process and it will probably cost more money, but it's just something to be aware of. In the last probably a quarter of these slides, we'll talk about kind of some of these more advanced concepts. And specifically, we'll talk about both agents as well as fine tuning. So I think a lot of folks might have heard about agents in the past year. There's been a lot of agentic projects that have also emerged. And it might be good to maybe understand first, what exactly is an agent? And the second piece is, how do we actually think about agents in the context of how it relates to what we just talked about, which is like RAG. The way we think about agents is they're basically LLM-powered knowledge workers that can not only read information about the world, but they can also do writes, right? They can modify state, they can perform actions. And so a workflow of an agent might look like the following. You might first have an action to read the latest emails, for instance, from your Gmail inbox. You might have another action to retrieve context, for instance, from your knowledge base. And this itself could be a RAG pipeline. So an agent could just be an outer layer that calls the RAG pipeline as a tool. It could analyze a file, right? Either with a RAG pipeline or with a code interpreter, depending on the file itself. And the final step is it could, given all this information, send an update. And this is something that actually mutates state. This could send a message on Slack. Implicit in this entire thing is that there's some sort of sequential decision making, meaning that a data agent is actually stateful, right, between actions, so that it can remember what's going on in between actions and use and store that in the state and use that to inform the next action that can actually take. The way we think about what we call data agents, right, and we call them data agents because we're mostly excited about agents in the context of kind of knowledge automation, is there's some core components. There's the agent reasoning loop, which can contain, this is basically the outer loop that will reason over what tools to use. And there's the tools themselves. The tools themselves can include API calls to different services. So you could, for instance, reason over how to send a message to like Slack API. Or you could reason about how to do a query something as a tool, like search Google, Bing, Wikipedia, or query or RAG pipeline. And of course, like one component here is the conversation history, not mentioned here, but in the diagram, being able to store state over time, right? And so on every action, you actually want to fetch stuff from your conversation history or memory in some way to help you inform what's the next action you're going to take. The agent reasoning loop itself, there's a variety of papers that have come out in the past year as well as the year before, as well as techniques and things that are a little bit more abstracted away. So for instance, like if you depend on OpenAI, for instance, OpenAI has now an assistance API that will handle this loop execution for you. They actually just hide the logic under the hood. And if you're just using their function calling API, you can actually just do a while loop over function calling, right? And the React agent is compatible generally with any LLM. This is a paper that came out last year. And this way of prompting LLMs to basically kind of decompose like a complex question into sub-questions, do chain of thought, and interleave reasoning with tool use. The tools themselves, again, can include query engine tools like RAG pipelines, so you can actually just query, existing pipeline as a tool. We also have a variety of different tools on Llama Hub. We have like 20 to 30 different tools now from a code interpreter, Slack, Notion. And these are all tools you can plug in as part of an agent. The way we think about any tool is it's just a Python class that you feed to an agent with a variety of different functions. And so it's very Pythonic. But the way the agent thinks about it is it basically treats it as an API interface. It has knowledge of the doc string, the arguments, and the LLM can actually, given the doc string and arguments, infer what's the right parameters to call each tool, right? Given that's going to call the tool. So maybe jumping ahead just really quick, how do you actually research and retrieve data from a knowledge base with agents? And this touches on using query engines as tools as part of an overall agent. There's different types of query engines that LlamaIndex offers, and these include traditional RAG pipeline setups like semantic search and summarization, advanced stuff like document comparisons, but also kind of other kind of interesting tools as well. For instance, we have, for instance, a text-to-SQL tool, or we have another one that allows you to actually combine structured data with unstructured data. All of these are essentially data tools. Some of them qualify more as RAG than others. In the end, it doesn't really matter. And if you plug these tools in as part of an agent loop, then the agent can reason about which tools you use given a task to actually try to answer the question, right? So the way we think about, honestly, how RAG extends to the agent setting is the agents is basically just an outer reasoning layer on top of the tool itself that can basically take in more complex questions and do stuff like chain of thought to actually answer the question. An example for this is financial analysis with like agents plus RAG. So given a question, like, compare and contrast Uber and Lyft's revenue growth, right? Well, again, looking at like the SEC 10K filings for both Uber and Lyft. This is another example where if you just feed this to a regular RAG pipeline, you'll likely not get back the right results. So compare and contrast Uber and Lyft's revenue growth. You try to get, for instance, like the top 4 most relevant pieces of context, you're not going to get back the right results. The agent will try to, or like the RAG pipeline will give you back some random context, maybe all Uber, all Lyft, and you might not be able to answer the question. On the other hand, if you feed this to an agent, the agent will actually break this question into sub-questions over tools, right? And it'll first break this down into sub-questions, break it into easier questions like, what was Uber's revenue growth in 2021? What was Lyft's growth in 2021? Each one might query a RAG pipeline itself, right? And that each sub-question will be more easily answerable via RAG pipeline. And then finally, once you get back these answers to these sub-questions, then you combine these answers at the end to get back the final answer. Some general things to think about if you're building agents, especially if you're building them in the context of RAG, is sometimes these tools or API services will give you back a lot of results. Some of these, like for instance, if you query like a Wikipedia page or even Google search and you try to load the entire contents of a web page, you're going to get back a lot of context. If you're working with limited context windows, a lot of times this will just overflow the context window and probably confuse the LLM. So one strategy here is if your tools inherently return a lot of data, try to figure out a way for them to, one, not return a lot of data. And some basic concepts that we offer include being able to index this data on the fly. So for instance, like given a lot of data, put it into some sort of vector DB first, and then have the agent actually take a separate action to query this on-demand vector DB. Another general principle and best practice if you're designing agents is to be able to handle a large, like figure out a good way to handle a large number of tools. Agents, even GPT-4 based agents, like the most powerful type available, tend to start failing once the number of tools goes beyond 5 or 6. And so if you have like hundreds or even thousands of candidate tools, just think about how to build an index over these tools and then do some sort of tool retrieval, retrieve the most relevant ones to actually pass to your agent. So if you have like 100 tools, try to first during query time, filter it out for the most relevant tools first, a candidate set of like 10 tools, and then have the agent pick out of that candidate set of 10 tools, like which ones to use given the user query. Skipping back really quick, an example architecture that we've done is this idea of a multi-document agent architecture. And this combines a few different advanced concepts, actually. We have both agents, but actually hierarchical agents, where you have like sub-agents as part of tools to other agents. And we did this because we wanted to explore advanced architectures to help tackle questions where there's certain questions that like standard top K RAG can't answer. And the solution here to build is just multi-document agents, right? Like there's certain questions like being able to get a summary over any subset of documents, being able to do proper document comparisons between different documents, being able to, for instance, do some sort of structured querying over the set of documents, and then like combining that with this unstructured data. And this architecture can basically handle these advanced queries by actually, in some sort of structured manner, given a query, break it down into a bunch of sub-questions over these documents, decide whether to do vector search or summarization, and get back the final answer. In probably the last section, I'll talk a little bit about fine-tuning. Right? So far, we've mostly focused on retrieval augmentation. Retrieval augmentation in the sense that, given the model itself, we don't train the model anymore. We just fix the model. And then we just, set up the right software tooling and abstractions, and of course, an evaluation data set to actually try to create a performant functioning system. And so in the last bit, I'll talk about fine-tuning, where what is the relationship between fine-tuning and RAG, right? Like what parts can we actually fine-tune to try to optimize performance? You can basically fine-tune a RAG system in 2 ways. You can fine-tune the embeddings. You can also fine-tune the LLMs. You can also fine-tune additional stuff like the re-ranker, as well as like, maybe even the retrieval algorithm itself, depending on what you use, right? But just for basic purposes, we can say we can fine-tune the embeddings and also fine-tune the LLMs. So the LLMs, the embeddings are a key part of this overall system, right? They affect the quality of your retrieved results. They're important for encoding the semantic context of your knowledge base. And a lot of times, if you just use an off-the-shelf model, especially if you're not using a paid service like OpenAI, if you're just using an off-the-shelf like Hugging Face model, they're not necessarily optimized to actually encode your data set, like your specific data domain in the right way. And that's precisely where potentially you might want to consider fine-tuning, right? And the solution that we propose here is generate a synthetic query data set from raw text chunks using LLMs, and use the synthetic data set to actually fine-tune an embedding model. This was proposed on a webinar by Joe from Vespa, and we were inspired to actually add some of these abstractions into LLMindex itself. But you can either have a human labeled data set to fine tune your embedding model, or you could have a synthetically generated data set. A synthetically generated data set basically means that you take an LLM, take in some input document corpus, and then given this input document, generate the set of questions from this document, and then map these question answer pairs as a training data set to your fine tuning algorithm. The next piece is fine tuning LLMs. And as we think about how do you actually fine tune LLMs and what can you fine tune, right, to actually lead you to better performance for these models or for this overall system, there's a few different aspects. First is that the weaker LLMs can potentially be bad. This is a typo at response synthesis, reasoning, structured outputs. Right. So if you're using stuff that's not GPT-4, if you're using a Llama 2 3.5 Turbo, they might not be as good in terms of generating a detailed answer, attending to the context within the answer, actually outputting something that's in a structured format like JSON. And so a solution here is you can try to generate a synthetic data set from raw text chunks, similar to before, right? Like use some guide, like parent LLM, like a teacher LLM, like GPT-4, to actually generate a set of candidate questions and then also generate the ground truth answers. And then given this as the guiding training data, try to actually fix all these issues like response synthesis, reasoning, structured outputs by just using this like kind of teacher data set as a training data set for your weaker model, right? So generate some sort of data set, whether it's to output structured outputs, output something else using GPT-4. And then try to actually teach like a student model to try to get better at its job. We have a variety of these abstractions within LLMindex. We have a full fine-tuning guide on both fine-tuning LLMs as well as embeddings, as well as cross-encoders. And so it's still in the pretty basic exploratory stages, but there's definitely some benefits that you can get by trying to instruction tune these LLMs further to better obey the task at hand. Some other examples include being able to handle custom instructions, like if you have prompts that you really need the LLMs to follow to adhere, for instance, to a certain style or to understand proprietary terminology within your data set. Those are also examples for fine tuning as well. Here's just some basic resources. This basically wraps up the rest of the talk. There's the production, here's a guide on just generally production RAG. How do you build more advanced stuff than just the basic stuff? And in the last section, which I don't have time to get through, here's just some guides on building basically a full stack application within LLMindex, right? And this basically completes it so that you basically have a functioning full stack application beyond just all these techniques I mentioned in the previous few slides. We have a bunch of tools to help you get started. All these are pretty much free, open source, MIT license, and so feel free to clone as you will. And if you're building LLMs in an enterprise setting or working with Gen AI, RAG systems, we love to chat. Here's some basic QR code, which will link you to an office hours form, but thank you.
Cool. Thanks a lot, Jerry. Maybe you have a question for, you have time for one quick question. For the person asking about the presentations, we will be putting it in Discord under the talk discussions channel, hopefully.
Cool. Sounds good. Do I just read? Do I read one of the questions?
Just put the highest voted question up on for you. So how would you process tables using RAG? Problems of splitting larger tables into chunks and framework recommendation.
Great. Yeah, that's a good question. I mean, framework recommendations, we have some of this stuff within LLMindex, so definitely encourage you guys to check it out. I think it depends. So for embedded tables within an overall PDF document, we actually have a bunch of tutorials for this because if the table is embedded within a larger document, it tends to be pretty small. And so there's no need to basically index it in like a SQL database, for instance. And the way I think about processing these tables is typically you get much better performance by extracting like a summary from it, for instance, using an LLM, like captioning the table versus embedding the table itself. And so, for instance, given a table of revenue, you probably want to embed the caption revenue, right? Or table of revenues, as opposed to encoding all the revenue numbers, which will confuse your embedding model and lead to bad retrieval performance. You can basically use the same technique that I mentioned in the slides, the recursive retrieval stuff, like the small to big strategy where you encode a reference to an underlying chunk. You can use that similar strategy to basically process embedded tables. For generally standalone tables, like just big structured data sets, which I guess I didn't really touch on during the talk, there's text to SQL, right? You can basically just like encode, like put it in a structured database and run some sort of structured query language against it.